We talked about this Ka stuff, we talked about this pKa molecule, and but how does that help us to get the pH of an acid that simply doesn't dissociate completely? How does that help us? Well, actually, it does help us. Because there is a sort of a rule of thumb that we can use. For weak acids, and a weak acid is usually defined as anything where the pKa is larger than 1. For weak acids, there is an equation. I could bore you stiff trying to develop this equation, but I think there is no point on a Friday afternoon doing that. Right? You agree? Yeah. So I just give you the equation for that. The pH for a weak acid is pH equals 1/2 of pKa minus log of the starting concentration of the acid. Yeah? This is an equation that I really want you to remember. pH equals 1/2 of pKa minus log of the starting concentration of the acid. Let's do a quick example for that. Okay? So we said earlier we have an HA with 100 millimolar, and this dissociates and produces 10 millimolar of protons. Remember that? This example? And we set the pKa of this guy equals 2.95. Yeah, 3. It's 3. Okay? So let's calculate the pH. pH equals 1/2 of pKa is 3 minus log of, we need to have that in molar, our 100 millimolar needs to be in molar because only then we can do a log, or then it is defined. So it would be log of 100 times 10 to the minus 3. And I close this bracket as well. If you ever write computer programs and forget to close a bracket, you know what's going to happen. The computer is not happy about it, and you get all sorts of weird and wonderful error messages. At one point, I just simply had to pull the plug out of the wall socket because otherwise the computer started to produce blue smoke, and that's usually not a good thing. So that's why I just closed this bracket. Okay, can we calculate that? What is log of 100 times 10 to the minus 3? Loud? 1. Is it 1? 2. What is log 100 times 10 to the minus 3? 1. 1. Okay. Sorry? Negative 1. Got it? Yep. So it's negative 1. So we have 1/2 of 3 minus negative 1. And that gives us 1/2 of 4. 3 minus negative 1 is 4. Half of 4 is 2. Yeah? So the pH of this acid is 2. And all we needed to do that, all we need to calculate that, was actually the pKa and our starting concentration. We didn't need any other information about that. Make sense? Of course, if we knew already how many protons we produce, then we could very easily convert that into a pH. We said we have 10 millimolar protons produced. And we can convert this proton concentration into a pH simply with this equation, pH equals minus log of 10 times 10 to the minus 3. What is this? Sorry? What is it? Minus 2, negative 2. So pH equals minus negative 2. And that is 2. But what if we don't know how many of these protons are actually produced? Fact is, we can't use this. And we have to go back to our beautiful equation for weak acids, which is this one here. Yeah? So for that, you only need to know the pKa, and usually you can look up the pKa for substances. People have determined that. You look up the pKa, you know how much of the acid you have used, and you can calculate the pH. Let's do a little example for that. We have acetic acid. That's what you put on your chips. Acetic acid has a pKa of 4.75. Strong acid or weak acid? It's fairly weak. Yeah? It's not terribly strong. And we have a 0.1 molar concentration. What is the pH? Over to you guys. Calculate the pH. You can talk to each other if you like. Yes, you're absolutely right. Yeah, I just heard you thinking aloud.
Sorry.
So pH equals half of 4.75 minus log of 0.1 So we have 1/2 over 4.75 minus, what is log 0.1? Thank you. Minus -1. This gives us together 5.75. And we want half of that. So that gives us 2.875. Or in this case, we would probably round it to 2.9. Yeah? That makes sense? This is actually also how you find the pKa of an unknown substance. Because you can do that in reverse. You have an unknown substance. And all you do is you measure out a certain amount. So let's say we have a 1 molar solution of this unknown substance, which gives us a pH of 5.7. Yeah? And I want to know what is the pKa of this guy. So what I do is I write down my equation. pH equals 1/2 of pKa. That is what I want to know, minus log of the concentration, 1. Yeah? That makes sense? So all I need to do is now rearrange this equation. The 2 goes over here, so I've got 2 times pH equals pKa minus log 1. What is log 1? 0. Okay, so that's 0. So I don't need to take care of that. And I know that pKa equals 2 times pH. And I said the pH is 5.7, so we have 2 times 5.7. And that gives me 11.4. Is that right?
I got the answer, but I did it a different way.
You got the right answer?
Yeah, but I did it a different way.
Okay. That's fine. If you get the right answer, not a problem. Sweet. So pKa of this substance is 11.4. Strong acid, it's a damn weak one. Right? It's much weaker than acetic acid. So that's a way, a neat way, how you can actually calculate or find out experimentally the pKa of a substance. So we can calculate the pH. It's a little bit like in primary school. I can calculate pH of strong acid. Tick. I can calculate the pH of weak acid. Tick. Oh, we've done a lot. Now, what happens? What happens when we actually have a mixture of a strong acid or an acid in general and its conjugate base? Because that is something that very often happens. So, can we calculate the pH of mixture of acid and its conjugate base? WTF is he talking about? Okay, let's go back to our dissociation equilibrium. So we said we have Ka equals H plus times A minus divided by HA. This is when our acid dissociates into H plus plus A minus. And that's our dissociation thingy. Do we have, in this Ka equation, do we have an acid and its conjugate base? What? Yes? Who said yes? Which would be, you're absolutely right. What is it? HA and 8 minus. This is a conjugate base acid system. So in a way, every time we have a weak acid dissociating into an A minus, and we still have HA left, we have this conjugate acid-base system in our solution. It's always there. If we have a weak acid, we have a conjugate acid-base system. Woohoo! So, who gives a damn about that? Actually, a lot of people do, because this is the stuff that keeps you alive. Yeah, I have to tell you that. This keeps you alive. This is important stuff. If it doesn't work, you are royally dead. I don't want to know what you thought. So, what do we do with that? Let's just simply try and calculate how we can get the pH of that. So first of all, we bring everything with the H plus to one side and everything that is not pH to the other side. So we would have Ka times Ha divided by A minus on the left-hand side, and that is H plus on the right-hand side. I just bring that here and that down here. Yeah, it's just simply rearranging an equation. Yeah, makes sense? Okay, and now here comes the dirty trick. We take both sides negative log. Now on the right-hand side, we have minus log the proton concentration equals minus log of Ka times Ha divided by A minus. Is that correct? Have I made a mistake? I hope not. Looks good. I know I look good. What is negative log proton concentration? pH. Equals, now we have to tame that beast. And we can write this also as minus log Ka minus log Ha over A minus. So in a way, we just multiply this minus log in, if you like. What is minus log Ka? Loud? pKa. Exactly. pKa. So let me write this down again for all the connoisseurs. We have pH equals pKa minus log Ha over A minus. And this Ha is the acid, and A minus is the base. Or some people call this the protonated form. And that is the unprotonated form. Does that make sense to you? Yeah? pH equals pKa minus log acid over base. And I probably should put that in a bracket. I told you, your life depends on this equation. And I show you why. And because this equation is so important, so freaking important, it has its own name. What was that? Did anyone say? Did I hear a name? No? It is the Henderson-Hasselbalch equation. Absolutely right. Well done. Henderson-Hasselbalch. Please don't call it the Hasselblad equation. Hasselblad is a producer of very expensive cameras. So it's Hasselbalch equation. Some people, especially when they are pissed, can't say Henderson-Hasselbalch. They just simply call it the buffer equation. This is the equation for, here comes the trick. This is the equation for a buffer. As the name suggests, yes, believe it. Well, what on earth is a buffer? A buffer is the combination of an acid and its conjugate base that allows you to keep the proton concentration, for example, in the cell, constant. Regardless of what happens to the cell, the proton concentration in the cell will always be the same, roughly, within certain limits. For example, it's not just the cell. In the blood, what is the pH of blood? Okay, what's the pH of blood? What did he suggest? 6 point? 6.4? What's the pH of blood? 6.7? 4? 4.8? This is the most important substance for you guys. What's the pH of blood? 7.4? Actually, the pH of blood is 7.2. 0.2 units. Or let's do 0.3 units. 6.9, and this bloody thing is back. 6.9, and on the other hand, 7.5. If you've got a pH in your blood of 6.9 or lower, or 7.5 and higher, you actually don't have to worry about the assessed practical. You actually don't have to worry about anything. You just have to worry about how comfortable your cloud is, where you're sitting on, because you're dead. Right? So, it is of utmost importance to keep your blood at a pH of 7.2. Just a slight change from this pH, from 7.2 to 7.5, That's roughly a doubling of the proton concentration. Just this tiny change will kill you. That's it. End of story. And there are some really, really nasty diseases around that have the tendency to change the pH of your blood. Any suggestions? What is a disease that can change the pH of your blood? Very common.
Diabetes.
Loud?
Diabetes.
Diabetes, exactly. In diabetes, you produce lots and lots and lots of acids through your metabolism. These acids go into the blood. What happens if you add acid to the blood? What will happen to the pH?
Increase. Decrease, right?
It will decrease, exactly. It will go down. But this going down will kill you. So how come people with diabetes are still alive? They shouldn't be alive, should they? If they produce acids and the pH goes down, they should be dead. How come they are alive? For a very simple reason. In your blood, you have a very powerful buffer. And it is predominantly made out of H3O minus. And what would be the corresponding acid? Carbonic acid, H2CO3. This is a system of acid and its conjugate base. It forms this buffer, and as a result, it resists changes in pH that are brought about by all these horrible acids when you have diabetes. That is why people survive diabetes, because they have got a buffer in their blood. Actually, okay, I don't get it. Why are changes in protons so bad? In a cell, for example. Does it really matter whether the cell has a pH of 4 or 8? Who gives a damn? Why is it bad? It's what? Loud? So, what's your name? Sorry? Izzy. Izzy suggested denaturing of enzymes. You're absolutely right. Absolutely right. But what does that mean? What does that mean? Enzymes work at optimum pH. Why? You're right, but why?
Long concentration environments can cause the structure of the enzymes to be disrupted and therefore break apart and not work properly.
James, absolutely right. What happens is if the protonation of a protein occurs, it can disrupt the three-dimensional structure of the protein. Why? I'm like a little child, huh? Why? 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 Why do we eat bananas? Why is a banana yellow? I had to go through that with my children, and it drives you completely potty. They always ask why, and I've learned to ask why. So, why is it bad for a protein to have protons around? What is a protein made of? It's amino acids. Many amino acids, all amino acids, have side chains. True? Some of the side chains of some amino acids can be charged. So, for example, this could be a side chain of an amino acid. Which amino acid could that be? Carboxy group, side chain, not the alpha chain, side chain. From a carboxylic acid, yes. What side chain, which amino acid could that be? Loud? Aspartic acid. The clue is in the name, you're right. And? Glutamic acid, exactly. So we have two negatively charged amino acids. So, in a protein, this side chain could form a bond with the amino group of another amino acid. So here we have a nice, let's do it like that. Yeah? So that would be what people call a salt bridge in a protein. Many proteins are held together by such salt bridges. They actually provide the scaffolding for the protein. And only if the protein has the right structure, it can do its job. Okay, now can you imagine what would happen if we add protons to this thing? What would happen? What would happen to our COO minus? Sorry, it? Oh, you didn't say? It would be not charged. It would turn into COOH. Yeah? What happens to our lovely salt bridge? Is there still a salt bridge? No, the salt bridge is destroyed. The protein is no longer held together. What happens to a protein that doesn't have the scaffolding? It unfolds. What happens to an unfolded protein? Can it still work? Bugger all. Yeah? There's no working. So just by adding protons to our protein, we kill it. If you add protons to your blood, you kill the proteins in your blood. They don't work any longer. An incredibly cool way of committing suicide is to inject half a liter of hydrochloric acid into your veins. It's pretty grim, but it works. The bad thing about that is your pain receptors in your blood vessels react to acid, to protons. The pain of killing yourself with that, so I have been told, is absolutely excruciating. And if you do that, you really wish you were dead. No pun intended. So please do me a favor, don't kill yourself with acid.
Just a quick question of what concentration would that acid be? I'm just curious.
It's a very good question, actually.
Because if that was the case, then like people would be committing murder with like highly dilute like acid and just injecting people. No, I don't know why my mind goes morbid, but it does.
You're absolutely right. Why don't people actually use this to kill other people? Yeah? I think we need to have a chat later on, right? The answer is, why doesn't it work properly when you just take a little syringe and inject hydrochloric acid? Yeah? The answer is because the average human being has about 5 liters of blood, which is a lot. And you have this guy. You have the buffer. And this buffer protects you from changes in pH. Let me be absolutely clear. It protects you from dramatic changes in the pH. There will be slight changes, but your organism can cope with that. So, when I said, take a little, don't. But with a little syringe of hydrochloric acid, it would be extremely and excruciating painful to do that. And it won't kill you because you have the buffer. On the other hand, if you inject half a liter of highly concentrated acid, that's it. So if you want to kill somebody, get a large syringe, get highly concentrated hydrochloric acid, or even sulfuric acid, battery acid, and inject that. Best way actually to inject that is a part where you don't have a buffer. It would be straight into the brain. Inject it straight into the brain, and you need less acid. It's much cheaper. But then, on the other hand, you need a strong needle to go through the skull. If you really want to kill somebody, right? If you really want to kill somebody, there are much nicer ways of doing that. Yeah? So don't go for the acid, please. And don't tell anyone that I suggested that. I probably have to delete the recording. Yeah? Now, how does a buffer work? What does it do exactly? How does it prevent you from dying when you have diabetes? I tell you that next week. Have a lovely weekend.